Nuclear binding energy. When the protons and neutrons combine to form a nucleus, the mass that appears, that is mass defect delta M, is converted into an equivalent amount of energy. That one is delta mc square. This energy is called the binding energy of the nucleus. So, binding energy is equals to Zmp plus n into Mn minus small m into c square. That one is equals to delta mc square. The binding energy of a nucleus determines its stability against disintegration. In other words, if the binding energy is large, nucleus is stable and vice versa. The binding energy per nucleon is given by Be upon A is equals to binding energy of the nucleus upon total number of nucleons. It is found that the binding energy per nucleon varies from element to element. A graph is plotted with the mass number capital A of the nucleus along the x-axis and binding energy per nucleon along the y-axis, as you can see in this diagram. Observations. First point, average binding energy of light nuclei like 1H1, 1H2, 1H3 is small. Second point, there are sharply defined peaks corresponding to 2He4, that is helium, 6C12, that is carbon, 8O16, that is oxygen, which represent that these nuclei are relatively more stable than other nuclei in their neighborhood. Third point, binding energy curve has maximum value in the range capital A is equals to 30 to capital A is equals to 140, corresponding to average binding energy per nucleon. That one is 8.5 MeV. The peak value of the maximum is 8.8 mega electron volt per nucleon for 26 Fe56. That one is iron. Hence, iron is the most stable element on the earth. Fourth point, as the mass number increases, the binding energy per nucleon decreases and gradually falling to about 7.6 mega electron volt per nucleon for 92 U238, that one is uranium. Hence, heavy nuclei are relatively less stable